Hello and welcome to the presentation of our project, Multi-Layer Gaussian Splatting for Immersive Anatomy Visualization. In this work, we focus on visualizing anatomical data obtained from CT scans. Traditionally, such data is viewed as monochrome slices. Three-dimensional rendering approaches, like those based on raycasting, improve visual realism, with the highest quality achieved through path tracing visualizations. Slice-based visualization excels at highlighting fine details with good contrast and minimal processing, and is the standard in diagnostics. However, 3D rendering, especially path tracing, provides a more intuitive and spatially meaningful way to explore complex structures. This makes it particularly useful for planning and education. Given these benefits, virtual reality seems like an ideal medium for viewing these visualizations. However, modern high-quality rendering methods are computationally expensive, making real-time use challenging. This brings us to our approach. Instead of rendering in real time, we use path tracing as an offline process to generate a faster intermediate representation. We explore Gaussian splatting for this purpose. Gaussian splatting allows us to approximate anatomical structures using thousands of small ellipses, which are automatically placed during training. This representation maintains high fidelity while significantly improving rendering speed. Our pipeline thus looks like this. First, we pre-render various views of our target anatomy from multiple angles in high quality with our path tracer. We then train a Gaussian splatting representation on these images. This representation can then be displayed on different devices via a rendering application, in our case the Unity game engine, where the Gaussian splatting data is imported and further compressed. You might have noticed that this approach results in a static representation. Unlike direct rendering methods, we cannot make dynamic adjustments. Changing transfer functions to highlight different anatomies, like viewing bone instead of muscle, is not possible without retraining. To address this, we introduce multi-layer Gaussian splatting. Instead of a single static model, we train multiple layers corresponding to different anatomical structures. This allows selective interaction with different layers, moving closer to the interactivity of real-time rendering. Let's say we render 3 layers, bones, organs, and muscles, as seen on the right. Our updated pipeline would now look as follows. We first pre-render multiple viewpoints for each layer. We then start training the first layer. As soon as the Gaussian splatting version of this anatomy is done, we train the second layer, using the images as well as the previously trained representation as input. This process is repeated until all layers are trained. We then export all layers together in a single Gaussian splatting representation, which we can view and interact with in VR on various devices. With our synthetic data experiments, we can see how this layering process works. By using the previously trained layer as static input and using adjusted pruning steps, the system learns to only include new information in each layer. For example, in this visualization, the third layer, adding green rings, primarily contains only these new elements and their shadows. This helps us create an efficient and lightweight layered representation with minimal redundancy. Through our Unity-based rendering plugin, users can interact with the trained anatomy by selectively toggling layers and cutting through them to reveal specific regions. This is particularly useful in planning and educational settings, where the relevant views are often known in advance. Our approach runs efficiently on both desktop VR and standalone mobile VR, with representations that are orders of magnitude smaller than traditional medical volume files. When comparing performance, Gaussian splatting renders a whole lot faster than denoised path tracing, while maintaining high visual quality. On desktop VR systems, our anatomy scenes render at well under 10 milliseconds. On mobile VR, frame rates remain reasonable, especially when not sorting Gaussians every frame, but when needed. In conclusion, we have demonstrated how our intermediate representation can outperform path tracing in performance and quality. Our layering approach adds some limited interactivity, though challenges like rough cutting edges and unorganized insides of trained representations remain. To support further research, we publish datasets with CT and synthetic data renderings for others to experiment with. Overall, our work suggests that such an intermediate representation is a viable solution for visualizing anatomical data in real time. Thank you for your attention. Please feel free to reach out with any questions or remarks. You can find all our datasets, code and trained models online on our project page.